Welcome to The Explainer. Today, we're embarking on a truly mind-bending conceptual journey. We are going to unpack a super dense, absolutely fascinating mathematical physics paper by Tristram de Piro called Some Arguments for the Wave Equation in Quantum Theory. Now, if you've ever found yourself just scratching your head at the sheer weirdness of quantum mechanics, well, you are in for an absolute treat today. This paper asks a massive, fundamental question about the very fabric of reality itself, and we're going to explore it step by step.
Okay, let's dive into this. Do we really need quantum weirdness? I mean, for a century now, physics has basically accepted that things at the microscopic level exist in these strange paradoxical states, right? Like being a wave and a particle at the exact same time. But the author here asks a really provocative question. What if a purely classical wave theory could actually replace standard wave-particle duality? What if we could explain the entire atomic world without any of those famous paradoxes?
Standard quantum theory relies pretty heavily on wave-particle paradoxes, probabilities, and the famous Schrödinger equation to explain how atoms behave. But de Piro suggests a totally alternative framework. He proposes that we might literally only need classical electromagnetism in classical wave equations to get the exact same predictive results. So he's basically proposing a strictly classical mathematical alternative to standard quantum mechanics. Section 1. The collapsing atom problem. To really appreciate why this proposed theory is so radical, we kind of have to rewind to the widely accepted failure of classical physics. According to classical electromagnetism, an accelerating charge radiates energy. Because of that, as Rutherford originally observed, if an atom operated purely like a classical tiny solar system, its orbiting electrons should constantly bleed out energy. They would inevitably spiral inward and just crash right into the nucleus. Honestly, if standard classical physics were the whole story, every single atom in your body should logically self-destruct in a fraction of a second. And, it wasn't just the collapsing atom. Classical theory also completely failed to explain black body radiation. This was known as the ultraviolet catastrophe, where classical math predicted that objects would emit literally infinite amounts of high-frequency energy. This specific failure was the exact catalyst that originally pushed physicists like Max Planck to invent quantum statistical mechanics in the first place. The classical rules just seemed utterly broken. But what if those classical rules weren't broken, but actually just incomplete? Section 2. The no radiation condition. Now, what's really interesting about this slide is how de Piro approaches keeping that classical atom stable. We're going to skip the heavy equations, but essentially, he starts with a continuous charge and current, and then applies what are known as Giffen-Menko's equations, which describe electromagnetic fields. Through a rigorous mathematical proof, he shows that it's perfectly possible to arrange a system where the magnetic field essentially just cancels itself out. Think of it like a perfectly balanced acoustic room, where the sound waves seamlessly bounce and cancel out any leaks, so absolutely nothing escapes. By using complex Fourier analysis, the author proves that you can isolate a very specific state where the magnetic field, and consequently the directional energy flux, are exactly zero. And hey, if the energy flux is zero, no energy is being radiated away, the electron doesn't spiral into the nucleus at all, the classical atom remains perfectly, miraculously stable. But the author actually goes a critical step further here. I mean, it's one thing to be mathematically stable while sitting perfectly still, but our universe is in constant motion, right? Well, de Piro impartially details a proof using special relativity to show that this no radiation condition holds absolutely true across all inertial frames. So no matter how fast an observer is moving relative to the atom, the mathematics hold strong. The energy remains completely locked in. Section 3. Confining the wave. So we've got a stable, classical atom, but that raises a huge transitional question for us. How on earth do we get discrete, jumpy quantum energy levels from a continuous, smooth classical wave? When you lock a classical wave inside a physical space, certain mathematical constraints just naturally happen. The electric current must vanish right at the atom's boundary, and the total charge has to be strictly confined within the spherical ball of the atom. To actually prove this works, the author utilizes some incredibly rigorous geometric mathematics, specifically Bessel functions and spherical harmonics, to show exactly how this containment functions. And this brilliantly illustrates how the math forces a continuous wave to become discrete. Think of plucking a guitar string. A completely free-floating string might vibrate in literally any continuous way. But the moment you pin it down tightly at both ends on the neck of a guitar, it can only vibrate at very specific frequencies, producing specific notes. Confinement creates quantization, naturally, without even needing new physics. Section 4, explaining the Balmer series.
Now let's transition to the absolute climax of the paper, showing exactly how the author's classical math yields undeniable real-world quantum results.
By enforcing those exact boundary constraints we just talked about, the mathematics successfully remove the continuous degrees of freedom. This forces the system's stored electromagnetic energy to settle into discrete, quantized levels. And the author points out that this directly mirrors actual observed phenomena, like the famous Franck Hertz experiment, where atoms are ionized and energy exchanges occur in highly specific quantized jumps, which leads to this massive aha moment. The Balmer series is this famous mathematical formula that correctly predicts the discrete spectrum of light emitted by hydrogen. And a core feature of the series is its dependence on the fraction 1/n², where n is an integer. Well, in this paper, de Piro successfully derives this exact 1/n² dependence using his purely classical no-radiation wave model. He basically proves that classical electromagnetism can indeed produce the signature fingerprints of the quantum world.
Section 5. A new classical reality. This brings us to the philosophical takeaway and the author's concluding vision for the true nature of physics. So, the crucial point is that this is a direct challenge to Schrödinger and the standard quantum model. Instead of insisting that a single electron is paradoxically both a particle and a guiding wave at the exact same time, de Piro uses non-standard analysis to suggest something very different. He proposes that what we call the wave might actually be composed of countless individual, infinitesimal entities behaving randomly and independently. Building on that, if you have a massive distribution of random, tiny, infinitesimal particles, their statistical distribution will naturally form a very sharp peak. De Piro suggests that our traditional experiments might simply be mistaking this sharp statistical peak for a single dual-natured particle. By viewing the wave as a distribution function, kind of like Boltzmann did for molecular speeds in gases, we completely avoid the need for those mind-bending wave-particle paradoxes altogether. Which leaves us with a final, massive question. Does classical electromagnetism still hold the undiscovered secrets of our universe? De Piro's paper builds a rigorously structured mathematical argument suggesting that, hey, maybe we abandoned classical physics a bit too early. By applying the right constraints and boundary conditions, the wave equation alone might be perfectly capable of explaining the quantum realm. It is just an amazing reminder that the fundamental nature of reality is still very much up for debate. Keep asking those big questions. Thank you for joining me on this explainer, and keep exploring.